The brain of all modern electronic devices, like this phone, is called the CPU, the central processing unit. This is made of billions of little electrical switches called transistors. These switches can be turned on or off just using voltage, which allows them to be turned on and off billions of times per second. As engineers try to make transistors smaller and smaller, they encounter problems due to a phenomenon called quantum tunneling. So, how does this work? To answer this question, we'll use a mountain analogy to have a recap of the classical mechanics involved, and then to see how quantum mechanics allows quantum tunneling.
Modern microtransistors are chemically etched on a piece of single silicon crystal. Silicon is a semiconductor. It conducts electricity under some conditions and acts as an insulator under others. Its resistive properties can be easily changed by adding different elements into its crystal structure through a process called doping. The source is where electrons enter the transistor, and the drain is where they leave. These sections are doped with phosphorus atoms, which raises the electron per proton ratio in those parts of the transistor. The central part of the transistor is doped with boron atoms, which lowers the electron per proton ratio at that area. This means that when electrons come through the source, they start passing from the phosphorus region to the boron region. After a while, the electrons in the boron region start repelling the new electrons trying to come in from the source. The transistor then starts to act like a resistor or a potential barrier. This is the off state of the transistor. A potential barrier is a region where the potential is significantly higher than the areas around it, so the energy required to pass through the barrier is much higher than the surrounding areas. This can be a high resistance area in an electric field, or a physically high place, such as a mountain, in a gravitational field.
So we can make this more understandable by visualizing the barrier as a mountain and electron as Ewan. Let's consider the case of Ewan trying to climb over a mountain. Ewan's total energy is equal to the sum of his kinetic energy and potential energy. Due to the law of conservation of energy, Ewan's total energy will stay constant, so as his potential energy increases, his kinetic energy will decrease. This is considering that there is no friction created while he climbs. If the maximum height reached is smaller than the height of the mountain, then Ewan will not be able to cross to the other side. So how do we allow Ewan to pass? We can lower the potential barrier, for example, make the mountain smaller.
In a transistor, this is done by applying a certain amount of voltage to the gate. This is the on state of the transistor. The gate of the transistor is made from copper and separated from the rest of the transistor by a thin layer of resistive silicon oxide. When a voltage is applied to the gate, the potential barrier gets lower, so more electrons can move into the boron region and leave the transistor from the drain region after that. If we were working with classical physics, our story would be over here, and we would have a perfectly functional switch. However, in the world of quantum physics, we have to account for quantum tunneling. This occurs because electrons travelling through the transistor act both as a wave and a particle at the same time.
To understand this phenomenon, we need quantum Ewan. While the location of classical Ewan can be known certainly by using classical physics calculations, the location of quantum Ewan, since he is very unpredictable, can only be guessed by using a wave function. The function is related to the probability of a particle being at any given point. The higher the absolute amplitude of the wave function at a given position, the higher the probability of the particle being there. As the wave function moves into the potential barrier, its amplitude decreases with an exponential decay. A higher potential barrier gives a faster decay. If the potential barrier is low enough and thin enough, it is possible that the wave function won't have decayed to zero once it reaches the other side, which means there is a chance of finding the particle on the other side of the barrier. So, even though quantum Ewan doesn't have enough kinetic energy to cross the mountain, he can tunnel through the mountain with quantum tunneling and appear at the other side even when you don't expect him to, just how you don't expect him at 9 AM lectures. You can picture it as Ewan digging through the mountain. He digs and gets very tired, but every now and then there's a chance he'll have just enough energy to make it to the other side. Quantum tunneling puts a physical limit on the size of transistors, because as transistors get smaller and smaller, so does the potential barrier that they create. This gives rise to the probability that most or even all the electrons tunnel through the barrier. This would make transistors stuck at a constant on state and effectively useless.